like me, most of us were actually involved in the original NASA DOE study back in the late 70s, including people like Gordon Woodcock and Ralph Nancy and Dick Nicholson and me. In those days, I was working for Peter Glaser at Arthur Little on the subject, and all of us have been working on it ever since. This group of followers, we called ourselves the Solar High Group, and what we've been working on is how do we make this thing, get this thing solved and get it done while some of us are still alive. What I want to talk about is mostly public relations and influencing politicians rather than technicalities, but we do need to look at the technicalities a bit. If I could have the wizard behind the curtain. Put up the... There it is. The first thing to think about is what sort of system should we be building? What sort of capacity should we talk about? Everybody thinks that solar energy is the ultimate renewable resource, but when we look at the actual forecast, this is a forecast by the Department of Energy Information Administration on the electricity consumption during the next 25 years. And the thing to note about this is the bottom red is the United States, and it's practically constant. There's a small increase in the rest of the OECD, but most of the increase is in the rest of the world, the non-OECD nations. And if you look at the generating capacity that's expected to be needed to supply this, there are some interesting things to see here. For the USA and for the rest of the OECD, there's very little increase most of the increases in natural gas. There's very little in nuclear or in coal. But if you look across the third world, you'll see that most of the increase is in coal. So what the DOE is saying is that the rest of the world is going to invest heavily in coal. There's also a considerable amount of hydro in the rest of the world because there are still good sites for that in the developed countries. Most of the good sites have already been taken, so the hydro is fairly not going to increase very much. The point I want most to make here is that solar electricity is represented by the barely discernible little yellow sliver at the top of each of these columns. It's very small. In fact, if we look at the technologies available, we can go nuclear, we can use coal, we can use natural gas, or we can use solar. The first three have their difficulties, which we all know about. The wind, I don't think, is going to go anywhere very much. It certainly has niche applications. I think this slide demonstrates it. This is a wind machine in Denmark. Note the size of the truck at the base of it. Note on the right is a gas well, a natural gas well that produces about the same amount of energy each year. The question is, which would you rather have in your neighbourhood? To produce the equivalent of a 2 gigawatt solar power satellite with windmills like this, we need 4,500 of them. So I think wind is going to remain, well, certainly going to fill niches, as the solar going to fill, terrestrial solar is going to fill niches. The wind is not a really viable competitor on a decent scale. Another issue is that we need to keep energy cheap. There is a movement afoot in this country to raise the price of energy, in particular the price of electricity, in the interest of making renewable technology more affordable, in particular to get carbon neutral technology moving. A problem with that, there are lots of problems with that. One of them, which I think is overwhelmingly important, is that if we increase the price of electricity here, we will not increase it in the third world because the third world is not subject to the same restrictions in terms of Kyoto Protocol as the rest of the advanced countries. So what we will do if we make energy expensive in this country is we'll encourage American industry to move to the third world where energy is cheap, and that will, the economic advantage we give to the third world countries will mean that they will be encouraged to make their electricity as cheap as possible since they don't care about carbon dioxide, which means that raising the price of electricity in this country is going to lead to more use, even more use of coal in the third world. And therefore, the net result of the program which is supposed to limit carbon dioxide would be to increase the amount of carbon dioxide produced globally. So I think it's a stupid policy. There are a number of niche applications, some of which we've talked about here, and some markets where you can sell expensive electricity, but I think we need to work to keep the price of energy, in particular the price of electricity, low, and it's a very hard metric to meet. The average wholesale price of electricity in this country is 5.7 cents per kilowatt hour. The average retail price is 11.5 cents. Those are numbers that we need to strive to meet if we're going to make solar power satellites a competitive technology. In 2009, solar electricity produced 0.3% of the electricity in this country, and the DOE says that by 2035 it might rise all the way up to 0.8% of the US electricity. These are, in other words, it's trivial. If we're going to use solar, we need to find a way to make it a serious competitor, a serious contributor to energy needs. And my goal would be to supply 15% of the new generating capacity that we will need worldwide in 25 years from now. That means 40 gigawatts of capacity in the States. The rest of the OECD, 60 gigawatts, and the rest of the world, 300 gigawatts. So that's a total of 400 gigawatts. We should be planning. We're going to be serious at all about solar power satellites. We should be planning for numbers like 400 gigawatts in 25 or 30 years. Here is I'll go very quickly here. This is a plot. Remarkably, the National Renewable Energy Laboratory has a record of the hour-by-hour solar irradiance at, I think, 1,541 places in the United States over a period from 1992 to 2005. So you can get the green curve here is their typical, it's been smooth because, of course, solar energy goes up and down every day. But the green curve is the seasonal variation in solar irradiance in Tucson, which is a good place to put a terrestrial solar plant. The red curve is the hour-by-hour load from the Electric Reliability Council of Texas as a utility. And the question is, how do you match these two things together? And to do that, what you have to do is to store energy one way or another. You either have to have an auxiliary power plant like a natural gas plant, but if you do that, you might as well use a natural gas plant all the time, or you have to store energy. And from these two curves here, you can work out how much energy you need in order to match the output at Tucson to this load, and the answer is like this. The red curve is the amount of storage, electricity, energy storage you need in order for Tucson to match ERCOT. And you see that you need for every kilowatt average power that you need something like 500 kilowatt hours of stored energy. If the blue curve is base load, that is a continuous 1 kilowatt all year round, then they need like 600 kilowatt hours for every kilowatt. That is to say, you must have a storage system which is capable of supplying the 1 kilowatt for something like 25 days. So it's a big storage system. And the only realistic way to do it, there are several options, but the best, most realistic way is pumped energy storage, pumped hydro. And that gets to be expensive. So when you go through all these numbers, these are calculating what it takes. It turns out that you need more than 40 square meters of solar array to produce an average of 1 kilowatt feeding the utility. And you go through the numbers and you end up with numbers like $19,000 a kilowatt just for the capital cost of the system without any operational costs, without staff costs, without anything else. And this is why, if you look at the annual energy outlook for 2010 from the DOE, it says solar technologies are too costly for widespread use in wholesale power applications. In other words, forget it. So the question is, what this means is the solar electricity industry is dead. Despite all the hype about it, it's not going anywhere. The solar power satellites, if we can make it cheap enough, power from space is the salvation of the solar electric industry on Earth. And I think what we should be doing is fact, the way that the solar energy industry has to go if they want to be a significant player in the world energy market. And here are go through the numbers, but I don't want to take the time. The challenge is to make solar power from space cheap enough. What this shows is the net present value of a stream of payments of a nickel per kilowatt hour as a function of the lifetime of the apparatus, whatever it is, and the real interest rate. The real interest rate is, of course, the difference between inflation and actual interest. It takes account of the fact that we pay a nickel for kilowatt hour of energy now. 10 years from now, we'll pay more. In the United States, the real interest rate has very rarely been over 3%. What this says is that if we can afford a nickel per kilowatt hour to amortize the capital cost of the solar power system, which is the sort of number we have to get to, leaving a little margin for operations and all the other stuff. We need to keep the price, the capital cost of the system down somewhere in the range of $6,000 to $8,000 per kilowatt. And the question is, can we do that? We need a lot of things which we've talked about, and I won't go through them in lack of time. The most important one, the one which makes everybody giggle when you talk about space-based solar power, is the cost of launch to Leo, which is currently is $5,000 to $10,000 a kilogram. But here is a deployment scenario looking at producing 400 gigawatts of power by 2035. The red curve, the black curve is the launch rate that we need to do that. I've assumed here that the weight, the mass of the systems which we are launching is 5.4 kilograms per kilowatt, which is a number that people believe that we can meet for solar power satellites as long as we use low thrust to get from Leo to here. What this says is that in order to meet this goal of 15% of world energy, the increase in world energy production, world electricity production by 2035, we need to be looking at launching something like 150,000 metric tons per year. That's a very large throughput. This is a conceptual design for a booster that Ralph Hanson and Ted Talley have been working on. It's Saturn V technology, and it's a biggie because it was a 50 tons payload, which I think is more than we should use. But if we're using this thing with 50 tons payload to launch the 150,000 tons we're talking about, we need to launch once every 3 hours. So you're talking about a very great throughput, an enormous throughput. We clearly need a launch site on the equator because it's the only place we can get a launch capability every 100 minutes or so. If we built this vehicle, we built as a fully reusable winged vehicle. If you put a non-reusable throwaway upper stage on it, you can raise it to like 100 tons for launching really heavy stuff occasionally. But when you look at launching on this sort of scale, hundreds of thousands of tons per year, and you look at the cost of doing so, I use the NASA cost estimating relationships and the masses of the vehicles to work out the costs included stuff for operations of a launch site and so on. What you see is that if we are launched on that schedule which I showed, eventually we'll get down into the range of $200 a kilogram. That all we need is a fully reusable vehicle, and all we need is a fully reusable vehicle, probably one like it, smaller than this, which gives even faster drop-off in cost. A fully reusable vehicle and the sort of throughput that is implied by any serious solar power satellite program means that we will eventually be talking about numbers in the $200 to $300 per kilogram range. And that's where we need to get to. It is certainly useful to look at niche markets that can afford higher launch prices in the near future. But they should be considered as part of a business plan that leads to this kind of volume. We'll not be able to get the prices down to where we're currently. This is just a net payback cash flow diagram, and finish up, my first point was let's present space-based solar power as an extension of terrestrial power, solar power, and not as a competitor. The second point I haven't talked about is that we should not take sides in the debate over global warming, because if we do, if we take sides, what will happen is that you'll annoy the people who don't agree with you. You don't need to make enemies out of either the skeptics or the true believers. I'm a skeptic personally, but I think we should stay out of that argument. We're perfectly right to say that the space-based solar power is a no-regrets approach to climate change, and that if it turns out that climate change is a global warming hypothesis is bunkum, then we won't have lost it. We'll have a nice energy system, unlike cap and trade or something like that, whereas if it turns out that we're wrong about global warming, we've spent a great deal of money and ruined the economy for no purpose. That's worth saying. It's not worth saying, as I hear many people say, we should avoid saying that we must have space-based solar power in order to combat global warming. Because if we say that, and if global warming then goes away as a problem, and I think it's going to, then we're very likely to have the interest in space-based solar power go away with it. Similarly, one last comment, we also need to be careful about talking about space-based solar power as the key to the extension of our civilization to the solar system. That is something which I think a lot of us who are interested in space-based solar power are really interested in, is get launched into space and then we can do all sorts of other wonderful things. The problem with that is when you say we need it in order to go out with the solar system, the vast majority of the public will think that's nonsense. Will think this is nonsense as well. So what we should be, here again, what we should be saying is perfectly right to say, if we build, say, space-based solar power, we will have a launch capability in the $200 to $400 a kilogram range, and everybody will benefit from that, including NASA and the DoD, and CONSAT launches and anybody else who wants to get into space. But we shouldn't make it the reason we're doing space-based solar power. And third thing, last thing is we need to work hard to make space-based solar power truly competitive with the other energy sources without all sorts of subsidies and things or else we're going to get there. At this point,